All right, so today what we're going to do is take a look at linear equation word problems as well as their relationships. So to start, we're going to understand what a linear relationship, and it's any relationship between two variables that creates a line when it's graphed on the xy plane. Linear relationships are very common in everyday life. Other frequent equations that we see are ones that are quadratic in nature as well as exponential. And later on through our lessons, we're going to look more closely at the similarities and differences between linear relationships, quadratic, as well as exponential models. But for now, we're just going to focus on some of the common trends and behaviors that we'll see within linear equations and their relationships. So our simplest linear equation is y equals x. That is what we call a parent function. And other than as an equation, we can represent it in a few different ways. If we take various input values that we'll refer to as the x values and we plug them into this equation for x, we evaluate and we'll get a corresponding value of y. Regardless of how simple or complex the linear equation is, we will get these ordered pairs. So these table of values can then be converted into ordered paired points that we see listed here. And then those ordered pairs will correspond to points on a linear graph within the xy plane, and then we can graph the continuous nature of this line and we can see more details about its overall trend. So again, every possible linear relationship is just going to be a modification on this equation. So when we're looking at dealing with linear equation word problems, there's a general 5-step process that we want to keep in our mind. The first thing we want to start with is understanding the problem. There's two parts that we want to understand. We want to understand more of a broad concept of what's happening, and it could be simple as looking at how much something would cost over time, or we could look at things such as motion over time and various different concepts. But it's in really broad terms, we want to think about and create a sentence that models our scenario. And then once we've figured out what our broad model is talking about, we want to look at more specific and what it is that we're solving for. What are we specifically solving for? And that's going to help us hone in exactly on what the steps that we're looking to use. And once we've identified what we're specifically solving for, that's going to lead us into our next step, which is going to be choosing a variable. Sometimes a variable is provided for us. Sometimes we have to come up with our own. Our variable is going to be some unknown value. But what's really, really important here is understanding what does the variable represent. What does the variable represent? Because if we don't know what the variable represents, then we're going to have a hard time putting our answer in a useful context and ensuring that either the model or the solution that we come up with is even valid to what the prompt is asking for. And then from there, we'll go ahead and translate. So hopefully either by carefully reading the equation or coming up with our own broad model, we're then able to translate it into a series of algebraic expressions and an algebraic equation that we can then use for the fourth step, which is to then solve. Now, not every question will have us solve. Some questions will specifically just ask for the model and only the model. But if we do solve, once we get a solution, it's always a good idea to also interpret our solution and to make sense that it makes sense, or to make sure that it makes sense within the bounds and the context of our situation. So we'll look at a couple different types of problems, and again, we're just going to highlight some key features. So we're starting with a car with a price of $17,000 to be purchased with an initial payment of $5,000 and a monthly payment of $240. Which of the following equations, and here what we're going to do is we're going to write our own, write an equation that can be used to find the number of monthly payments M required to complete the purchase, assuming that there are no taxes or fees. Okay, so many of these types of questions where they're asking for an equation, they will be multiple choice style questions, so you won't have to completely write it from scratch. But if we can write it from scratch, then identifying it from a list will be easier. And also it really helps us to hone in on the details of what is actually being talked about and what these different features and how they're represented within the equation. So the first thing we want to do is understand what's our broad model. Okay, so the broad model is that we're buying a car. So car costs. So we have a total car cost. Okay, costs for a car. Okay, so we have the total cost for a car, and then we have to think about, okay, well, what is that cost comprised of? Because we have a couple different dollar amounts here. Well, when you buy a car or you make any large purchase, there's usually a down payment, and also called an initial payment. So we have a down payment. That's the money that you put down before you walk out of there with whatever your heavy purchase is. So the total cost for a car is going to be the down payment. And then over time, we're going to have to make multiple monthly payments. Multiple monthly payments. Okay? And so all of those together are going to add up to the total cost of our vehicle. So we've come up with a very broad statement for what's going on in this model. The total cost for a car is going to be a combination of the down payment and the multiple monthly payments that we make thereafter. So then we kind of want to look at, okay, well, what are we solving for? Well, in this case, we just need to identify an equation. So all we're doing is writing an equation that models the scenario. So let's go ahead and continue to build that equation. The next thing we'll need to do is choose a variable. And in this case, a variable is provided for us. So we don't have to choose one. We just need to make sure that we can identify that M represents the number of monthly payments. M represents the number of monthly payments. So we've got our variable. Let's go ahead and translate. And so now we can break down this sentence that we wrote into little segments and pull information from the prompt so that we can form our equation. And so we'll start with the total cost for a car. The total cost for a car, that's the first part that we have. And we can see that we're given that right there in the beginning of our equation. The total cost for the car is $17,000. Is a common phrase used to be equal. Okay, is the same as, equivalent to. These are terms that we use to represent equal. And then we have a down payment. That's our initial payment of $5,000. So $17,000 is equal to $5,000. And is another expression that often means sum or plus. And then we have multiple monthly payments. So we know that the multiple monthly payments are going to be $240 each, and we don't know how many monthly payments there'll be, but that's what our variable comes into play. And so when we're making $240 monthly payments every month for some number of months, we end up multiplying those values together, so 240M. Now this gives us the general structure for our equation, and we can see that we have 17,000 equals 5,000 plus 240M. Now, we have an equation. There's our model. Now, when we're looking at multiple choice questions, our equation may not look exactly, or our answer options may not look exactly like what's been provided for us. So we need to understand a few key things. First and foremost, we need to understand the different parts of an equation. Here we have a coefficient attached to our variable. This is always going to be what we call the rate of change. And as we rewrite and manipulate our equation, if we understand that that coefficient is our rate of change, we can see an equation in a slightly different form that still fits this model that we have. For example, I could rewrite the equation as 17,000 equals 240M plus 5,000. Okay, we could use that to represent our situation, or we could even adjust it in various different ways and switch it all the way around. 240M plus 5,000 equals 17,000. Okay, those are some very basic changes. We may also have the equation solved for M, and we'll talk more about that when we cover literal equations. But we could also rewrite it in a form where we have 17,000 minus 5,000 divided by 240 equals m. So one of the things you'll want to do is be very comfortable with identifying key parts of an equation and how those numbers will look in the general structure. You'll also want to be comfortable with rewriting and manipulating the equation in whatever method suits your needs best, and noticing that all of these equations that we just wrote are equivalent equations. The other key parts that we want to look at is that we have a constant, which is our initial value. That's that $5,000, and that's generally a starting point that we'll see within various equations. So we've got a basic equation and we've got a few different models, and so when we're looking at a multiple choice question, we usually want to pick the option that just looks the best or the closest to what we have, because it may be written in a slightly different form. Our next example is same idea but a slightly different vein. We're looking at the width of a rectangular vegetable garden is W feet, and the length of the garden is 8 feet longer than its width. Which of the following expresses the perimeter in feet of the vegetable garden in terms of y? So our broad understanding is that we're solving for, or we're representing and modeling perimeter. We're modeling perimeter. And on the SAT, your formulas are going to be given, and you won't need to memorize the geometric formulas. They'll either be given on a reference sheet or they'll be given in the question. And so a couple different ways that perimeter can be represented as either P equals 2 times the sum of the length and the width, or if that is distributed, it could be 2 times the length plus 2 times the width. Either of those is fine. So if we look at perimeter is equal to 2 times the length plus 2 times the width, let's say this model here. So that's our broad, and what we're looking for and trying to solve is we want to express this formula in terms of W. So that means we don't want any other variables, we just want W as the only variable in our equation. And so that means we're going to have to rewrite this equation so that L is not included in it and it needs to be replaced with something else. So then we go and look at our equation. Our variables are defined, length for L and W for width. That's given as part of the formula. So we can go ahead and translate. Well, we have another statement here. The length of the garden is 8 feet longer than its width. So the length is 8 feet longer than the width. And this question, or this statement, is very important because it's a statement that we can use for our translation portion. The length, represented by variable L, is equal to 8 longer than, so more than, the width. The length is going to be 8 feet longer than the width. And so now we actually have something that we can use to replace our variable L with. Actually, let's go ahead and write that as just W instead of the width. So we have 8 plus W, and we can use that to substitute in for the variable within our formula. And so with P equals 2 times L, instead of L, we're going to use 8 plus W plus 2W. We've replaced the L with 8 plus W. And that's what we did over here. So now that we've essentially written the perimeter in terms of W, we may need to rewrite or simplify the equation so that it matches up with whatever answer options are given. So we can use distributive property as well as combining like terms in order to get a simplified yet equivalent form of the equation. Again, we didn't need to solve for anything other than just writing an equation that models our scenario. This last one, we have a concession stand at a high school baseball game that sells peanuts for $2.50 a bag and hot dogs for $3. The concession stand brought in $196 and they sold 42 hot dogs. How many bags of peanuts did the concession stand sell? So our broad statement is that we are selling peanuts, and we are selling hot dogs to earn money. Okay, we're selling peanuts and selling hot dogs to earn money. And so now we can go through and look at what is it we're trying to solve for. Well, we're trying to solve for how many bags of peanuts were sold. When we're asked for a specific value, such as how many bags of peanuts were sold, that usually will be your variable that you have to solve for. So we can define our variable as P for bags of peanuts. And so now we've defined our variable, we can go through and start to kind of fill in our equation and use that in order to solve. So let's go ahead and translate. So when we're selling peanuts, we have some number of bags of peanuts, and for every bag of peanuts we sell, we make $2.50. And so we can use the multiplication relationship of 2.5 times P, and plus we are selling hot dogs, same thing. For $3 a hot dog, when we sell 42 hot dogs, that product is going to tell us how much money we made selling hot dogs. And then to earn money, well, how much money we make selling peanuts plus how much money we make selling hot dogs is going to be equal to our total revenue, which in this case was $196. So now that we have our basic equation, 2.5p plus 3 times 42 equals 196, we can go ahead and solve for p. 2.5p equals 126, plus 126 equals 196. Subtract the 126, 70, and then divide to get 28 bags of peanuts. Now, let's look at more broad terms of the forms of linear functions. And if we compare these to the previous two questions, or the previous three questions, we should see some similarities between these different forms. So starting with the slope-intercept form, this is one of the most common. We have y equals mx plus b, where m represents the slope, also known as the rate of change, and b is the y-coordinate of the y-intercept. Most often we use this when we have word problems that have a singular input and a singular output. So when we looked at the previous example of when we're buying a car, or when we're looking at the rectangular garden, when I input a specific width, that is going to determine as my input what the perimeter will be, which is my output. And this is very similar to that y equals mx plus b. If I didn't know how much my car was going to cost, my m would be the input, and then the cost would be the output. If that value was unknown, we again would have an equation in slope and intercept form. So it's very useful when we are identifying rate of change or a starting point, or that we're given those values of information. What is the rate of change and the starting point? We can write an equation based off of that pretty quickly. Standard form, on the other hand, is very similar to our peanut and concession example. So notice how in this version, the variables are on the same side of equation, x and y, rather than x and y being on opposite sides. A, B, and C are real numbers. A and B both cannot be 0. One of them can, but they both can't be. And a lot of times in word problems, we'll see this type of notation when we have two input values. And so instead of having an input and an output, or an independent and a dependent variable, we have two independent variables, and then some combination of them gives us a total. So when we're dealing with equations in standard form, it can be very useful to identify x-intercepts and y-intercepts. And then again, with the types of equations where we have two different inputs. So let's look at a few more examples and kind of compare the different notations that we use. The table to the right shows the shipping charges for an online retailer that sells used textbooks. They tell us that there's a linear relationship. We'll be able to find that on our own if we needed to, and we'll discuss how to do that in a later unit. But they went ahead and told us, hey, this is linear. So we want to actually be able to write an equation in slope-intercept form, which is the y equals mx plus b. And we want to relate y, which is our shipping charges, with x, the merchandise weight. So in order to write an equation in slope-intercept form, we need two things. We need, as the name states, the slope and the intercept. So we'll start with slope. Slope is measured as the change in y divided by the change in x. And so arithmetically, what we do is we write that as a difference. y2 minus y1 over x2 minus x1. And that gives us our rate of change over those 2 points. So to calculate, we're going to look at our table of value. We've got x and y values, and we can pick certain ones to be 1 and 2. It doesn't really matter. Arbitrarily, I'm going to go ahead and say that this is x1 and that this one is y1. y1. This is an ordered pair. And then this will be x2 and this will be y2. It doesn't matter which two ordered pairs we use. We could have used the third one instead if we wanted to. But as a general rule, I like to try and use the smaller values if I can, just in case it makes anything easier. So we can set up our formula. And so we've got these values identified as y2 minus y1 and x2 minus x1. So we get 7.5 over 5 with our subtraction, which simplifies to be 3 halves. So we get 3 halves for our fraction, or 1.5 as our decimal. So our slope is 3 halves, or 1.5. So now that we have our slope, we can go ahead and move on to identifying our y-intercept. So recall that our y-intercept is the y value. So y-intercept is the y value when x is 0, which again is often referred to as the starting point when we're dealing with a lot of word problems, because generally our independent variable doesn't go in the negatives for many types of word problems. When we look at our table, we see, well, we don't have a x value of 0 and a corresponding y value. So we can't use our table. We'll need to find it on our own. So what we have is a equation that we can use to find our y-intercept, because the y-intercept is the b value. If we look at the equation y equals mx plus b, what we can do is identify that, well, let's take any one of our ordered pairs in our list, let's plug in the slope that we know, and let's solve for b. And so that's what we're going to do. We'll start with our slope of 1.5, and then we're going to use an ordered pair from our table. And I'm just going to take this ordered pair, 5, 16.49. So if I'm going to take 5, 16.49, and I'm going to use that as my ordered pair. The y value is 16.49, the x value is 5, and now what we can do is solve for b. So 16.49 equals 7.5 plus b, and then when we subtract, we get a b value of 8.99. So now that we have the slope, and we have the y-intercept, now we can write our equation in y equals mx plus b notation. That's our slope-intercept. Now another equation that's similar in structure, we have the equation that's written here, and the prop states that Lawrence will mix X milliliters of a 10% by mass saline solution. So X equals the milliliters of a 10% solution. The rest of that's pretty verbose. We don't need to really look at all of that together. We just want enough to understand X is the number of milliliters of a 10% solution. And Y is the milliliters of a 20% solution. So Y equals the milliliters of a 20% solution. And in order to create, they mix them together in order to create a 12% mass by saline solution. And we can see each of these parts represented in our equation up here. We have the 10% mass solution here, 10% written as a decimal notation times X. We have our 20% solution. And then when we go ahead and combine them to get our 12% by mass saline solution, we see that combination here where we have the total volume of the two solutions mixed together, and we end up with a 12% mixture. So we're told that this equation represents the scenario. If Lawrence uses 100 milliliters of the 20% by mass saline solution, how many milliliters of the 10% mass saline solution must he use? So this is what we want to solve for. How many milliliters of the 10% solution? And we have something that represents that, our X value. So we want to solve for X, because X equals our milliliters of 10% solution. The other part of this equation is that he's using 100 milliliters of the 20% solution. So Y equals the milliliters of the 20% solution. And he told us that he's using 100 milliliters. So we can actually substitute this value in for Y. And then once that's substituted in, we can go ahead and solve. So 0.10x plus 0.20 times 100 equals 0.12 times x plus 100. We'll multiply and use our distributive property to give us, that should be 20, not 200, to give us the following equation. We can isolate our variables to one side and subtract from the other, and divide to get an X value of 400 milliliters for the amount of the 10% solution. And this answer makes sense because if we look, these are on very similar scales of magnitude, 400 milliliters and 100 milliliters. It would make sense to mix somewhat close to the same amount so that we end up with the proper solution. Now the next few I included are some multiple choice so that we can look at how different answer options are presented. So again, we're given another equation. The equation above models Y, the amount in dollars charged by a website hosting service to host a website for X months. The total cost consists of a one-time setup fee plus a monthly charge for hosting. When the equation is graphed in the XY plane, what does the y-intercept of the graph represent? So we're solving for y-intercept. And they want to know, what is the context? Well, one of the first things that helps is to look at the equation and see, okay, well, what is the y-intercept? Well, the y-intercept is 550. Well, since we know the numerical value associated with the y-intercept, because we're comparing it to our y equals mx plus b notation, we can eliminate any answer that doesn't refer to this value. So we can get rid of answer option B, and we can go ahead and get rid of answer option D. So we're left with options A and C. And the only difference is how they're phrased and what they would represent in this context. So a setup fee only happens once. So it's a one-time charge. And if it's a one-time charge in an equation, that's represented as a constant. Versus a monthly charge, that happens several times. And so when something happens several times and it's repeated, that's usually part of our rate of change. And so when we look at our equation with the 550, and we know that it's a y-intercept, we want to think about, is the y-intercept a one-time charge or in a constant, or is it a rate of change? Well, up here, the rate of change is 35, not 550. 550 is a constant. So it makes the most sense that answer option A is going to be the meaning of the 550 within our equation. For example D, we have a farm that purchased a combine harvester valued at $330,000. The value of the machine depreciates by the same amount each year, so that after 10 years, its value will be $80,000. Well, even if you don't know what the word depreciate means, we can kind of get a context that we are starting at $330,000 and we are ending at a value much less than that. So depreciates must mean something along the lines of goes down in value, and we are correct in that assumption. So even if you're not familiar with the word, we have enough context in the question to be able to figure that amount. So which of the following equations gives the value V of the harvester in dollars T years after it was purchased? And so what we want to do is we want to look at the equations, and based off of this depreciation, that it goes down in value, we can eliminate answer C because that one has addition in it. So we can go ahead and eliminate answer C. That one's not going to work for us. We've also identified that 3,300 or 330,000 is our starting value, and that helps us actually eliminate V because, or answer option A, because this one does not start with $330,000. It starts with $80,000. And so then we have two other equations that we want to look at and we have to compare. So the only difference between these equations is the coefficient, all right, the amount that's being depreciated every year. Now remember that $80,000 is our ending amount, not our rate of change. And so it wouldn't make sense to have the rate of change listed as the ending amount. That's very unlikely that the ending amount and the rate of change are going to be the same. And so it's probably going to make most sense that B is our solution. But what we could do is we can actually double check it real quick. So quick math, 10 years, after 10 years, the value will be $80,000. So if 10 is our value for T, we can substitute it in and see what is the value after 10 years if we use this equation. And if we go ahead and substitute in 10 and multiply, we're left with 330,000 minus 250,000. And that subtraction is indeed $80,000 as the ending price. So this answer makes the most sense. So we're going to go with answer